Okay, so I'm going to introduce our speaker. It's interesting. I sort of vaguely knew of his work over the course of a number of years, and then a while ago, Michael Lesk pointed out the Building Rome in a Day paper, which I looked up and read, was just amazed by, and then back in April, I was invited to go up to Cornell and give a lecture about the Google Art project, which I did, and I mentioned the Building Rome in a Day stuff, which I was very impressed with, and there was tittering in the audience. And Noah was right there because, of course, he was there, and I met him then, and I said, "Oh, you got to come and give a talk here because the stuff that you do is really quite amazing." He's an assistant professor at Cornell in the computer science department, working on computer vision and computer graphics. He did his undergraduate at the University of Arizona in computer science and math. He got his Ph.D. from UW. For those of you who don't know that, that's University of Washington. A trick question for you, which I won't ask him now, is has he ever seen Mount Rainier from Rainier View on the campus? Because even though he may have spent a while at Washington doing his PhD, you rarely ever see Mount Rainier from Rainier View. And then the final trick question is, why are there cherry trees on the campus at University of Washington? So, Noah.
This is great. Thank you so much. Why are there cherry trees at University of Washington?
Well, when the Emperor of Japan gave a large gift of cherry trees to the new Republic of the United States, he sent them to Washington, and the ship captain delivered them to the Washington he knew, which was the state of Washington.
That's great.
And the governor had them installed on the campus. So another set was sent to Washington, D.C.
I think we should just have a talk of you giving cool anecdotes. But okay. Hey everybody, thanks for the introduction, Mark. Yeah, I'm Noah Snavely from Cornell University, and I'm going to be talking about what I've been calling the distributed camera, which is sort of that camera that exists by virtue of millions of people around the world having cameras and taking pictures all the time and uploading them to where all of us can access it. So it's sort of this virtual camera that you have to use your imagination. But so if you have questions, please feel free to ask them. I'll try and repeat them if there's questions during the talk. But yeah, this is informal, so just please feel free to speak up. So, it's no surprise we're living in a world where pixels are very cheap and very available. So there's, I'm sure, trillions of photos available online, millions more uploaded every hour. These are interconnected. Many of us have access to many of these photos. And so it's really the case that the internet is becoming this unprecedented visual record of our world, and it keeps growing. So anytime something interesting happens, there's probably a photo of it or hundreds of photos of it uploaded to some website, Facebook, Flickr, Picasso, whatnot. So, you can see facts attesting to this. So this is the SEC filing that Facebook did recently. I don't know if anyone here has Facebook stock, but before they had to do that, they had to file with the Securities and Exchange Commission. One thing they put in there is that over 300 million photos are uploaded per day on average to Facebook on the 3 months ended March 31st, 2012. So that's a lot. But I think my guess is that the biggest source of pixels out there is YouTube. So this is a year ago where evidently 38 hours of video were uploaded to YouTube every minute. So 48 hours, so 2 days. That's amazing. I don't know what that is, but maybe some people here can enlighten me. But it's a lot of pixel data. It's amazing. It's just mind-boggling. And the year later, that was now 3 days of video every minute, and they're very proud of that. But it's just this massive influx of image data, right? Documenting many, many things: cities, people, events. It's an amazing source of data. So I'm very interested in sort of finding ways to make use of this data to better understand our world. This very, very unorganized data. Okay, so there's many things you could imagine doing with this. Some sort of sneaky and some maybe more positive things. So the city of London has tens of thousands of closed-circuit TV cameras all over the city, taking pictures of things. And you can do things like, if there's a riot, as there was in London a few years ago, find pictures of suspects and put them on the internet for people to look at. So that's one sort of outcome of having images everywhere. In this case, it's cameras that were intentionally put there by the government. But you can imagine that you could also do this with just random pictures that people take all the time. So, maybe this could only happen in New Jersey, but a few years ago, there was this news article which, a thief was caught because they were stealing a camera, and they were caught in another camera that was taking a picture of the scene at the same time when this crime was happening. And so they were able to, connect the dots. I meant, someone at CSI was probably looking at all these photos, and they happened to find this one and, figured out who was doing this. So, that is sort of a coincidence that this happened, but you can imagine as more pictures are taken, there's sort of this surveillance camera that's just out there in the crowd, all documenting everything that's taking place, or many things that are taking place. So, okay, so you can use this potentially for sort of forensic applications, this distributed camera. You can use it to sort of figure out what people are doing. So this is work that was done by some of my colleagues at Cornell a few years ago, including Dan Huttenlocher, who's now running the New York City Tech Campus, building that. But what they were doing, they downloaded millions of geotagged photos from Flickr and just tried to figure out what they could tell about people from these images. And one of the most basic things is where people tend to take photos. So what they did is they clustered the images into the top 15 or top 20 city-scale clusters, and then within each of those city-scale clusters, they clustered into landmark-scale clusters and figured out sort of what the most photographed cities on Flickr are, and within each city, what the most photographed landmarks are. So here's, I think, the top 20 most photographed cities in North America, and within each, it shows a picture of what the most popular landmark is. So, New York City, where is it? Manhattan. The most popular landmark is the Empire State Building. I think that's a picture from the Empire State Building and not of the Empire State Building. That's my guess. And Fenway Park is the most popular landmark, according to Flickr users, in Boston. And the city of Disney World, the most popular landmark is the castle. Okay, so these tags also come from people's tag, Flickr tags. So this, it's maybe not completely accurate, completely representative sample of people, but this gives you sort of insight in how people and where people take photos. I think the third or fourth most popular landmark in New York City is the Apple Store. Where's the Apple Store? The iconic cube one. Okay, yeah, that one. And so photographs have always been also a tool for science. So especially measuring how things change, you can do that in a very compelling way with photographs. So here's two photographs taken many years apart of a glacier, and you can tell something's changed between them, and that communicates a lot of information. So that's what you can do with two photographs, but imagine what you can do with millions and billions of photographs taken all the time all over the world. So here's just a few sample photos of the city of London, a few of many, many millions on Flickr. And you can imagine what could you do if you had access to all the photos ever taken of the city of London. What kinds of things could you figure out from those images? Well, you could possibly create the most compelling visualization of the city, show it from any viewpoint, from any time of day, any season. You could potentially figure out how the city is changing over time. What buildings are going up, how the buildings are changing, how people move through the city differently, use the city differently. Maybe all that information could be gleaned from these photos. Perhaps you could also monitor the environment or do sort of science with these photos. Sort of answer questions like, is spring getting sooner every year? Can you tell that from these photos in various parts of the city? Are flowers blooming earlier in the year? That sort of thing. And as I mentioned, forensics, could you answer other questions like, who stole this thing from this part of the city at this time? These are all potentially things you could imagine answering with all these photographs that are being generated all the time. So this is not, there's other domains in which this sort of thing is taking place. There's this notion of sort of citizen science where you actively as a citizen get involved in scientific sort of process. So at Cornell we have the College of Ornithology, and you can go out and see birds and record where and when you saw them, and then enter them into a database, and therefore be helping with tracking birds. NASA has a bunch of these. One of the most famous is Galaxy Zoo, where you can go on sort of, it's sort of a game, but you go and you learn to label galaxies, and they have hundreds of millions of galaxies that they need to label, and so you can help with that process. So more closer to what I'm going to be talking about, computer vision, how can we use computer vision to solve this problem or get useful data from these images? This has been going on in astronomy for a while now. So there's this really cool project called astrometry.net that was done partly with some of the astronomers at NYU and also Sam Royce, where they could take any photo of the night sky, through a telescope, taken by any amateur astronomer, and figure out the exact camera parameters of that image and figure out exactly what you're looking at. So, for instance, there's an astrometry.net Flickr group where if you post a photo to that group, the robot will get that photo, suck it up, figure out the parameters, what field of view, where in the night sky this is, and then label it and, circle things of interest in that image, like what galaxy or globular cluster you're looking at or nebula. And it does that completely automatically, just by using computer vision to tell what stars you must be looking at based on their configuration. It doesn't need any metadata at all. And so, you can start doing some interesting things. You could sort of take photos that were never intended for science, perhaps, and use them to do interesting things. So some astronomers showed that you could then use sort of crowdsourced, just amateur astronomy photos posted on Flickr to do things like track or calculate the path of a comet. Okay, so that, it's not quite maybe Nobel Prize winning science yet, but it's sort of a start, and you can sort of imagine the kinds of things you might be able to do if you could tap into this huge set of photos that are being generated. So the question is, can you do the same thing, not with sort of astronomical photos, which are sort of constrained, since the night sky is sort of 2D, and do it with photos taken anywhere in the world? Okay, that's sort of one question I'm very interested in. So, there's a bunch of applications. Here's another one. I was talking to some of the facilities folks at Cornell, and at Cornell we have these old buildings, built in the 19th century, which are moving apparently by a few millimeters every year. Just sort of the walls are starting to buckle or whatnot. And they're interested in sort of monitoring that. How much is the building changing over time? And so you can imagine trying to do that sort of measurements. If you could do very accurate measurements from photos that are just being uploaded over time, you could avoid the expense of what they're doing right now, using laser scanners every so often to do very precise measurements of these buildings. Okay, so it wouldn't be cool if we could just use all the photos posted on the internet to do these kinds of things. And the big problem, of course, is that there's no order to this data at all. It's just pixels. It's very uncalibrated. You don't necessarily know where a photo is even taken or what time it was taken. And those are sort of very important things if you want to sort of use images to make measurements or tell that something happened in the world. From a computer vision standpoint, that's the kind of problem I've been trying to tackle over the past few years through the lens of geometry. And I'll talk more about that as we go through the talk. So what we'd like to be able to do is for any photo on the web, figure out exactly where it was taken, figure out the exact camera parameters. So where in the world was the camera center? What direction was it looking? What was the focal length? What are the radial distortion parameters? We want to map a pixel in that camera to a ray in 3D space, so we can say, what exactly would this ray hit if we actually cast it in a world coordinate system? We also want to know exactly what time it was taken, hopefully with second precision. What is visible in the image? What objects can we see so we can compare them to other images of the same objects? So what we want is something that will tell us this photo was taken exactly here, looking in this direction, and the time is October 8th, 2011, and that this is tree number, if you have some global index of trees, this is tree number something, some big number, and you can probably guess where this is taken, most of you. And these pixels correspond to a particular building. So then you can do queries like, show me all the images that show this building from this time to that time, or show me the images of this particular tree in Central Park. Okay, that's the kind of thing we'd like to be able to support, just with all the images in the world. The sort of guiding principle here is that we're going to, this involves geometry in a very fundamental way. We want to know the geometry of this photo very accurately. So, there are ways of getting approximations to this information. You can use GPS and timestamps, as many photos have increasingly. But, in my experience, these are very noisy for a number of reasons. It's not unusual to find a photo that, for instance, is taking northeast. You can work it out on a map, but the GPS or the compass information says it's pointing due south, which, that's not a useful measurement if you want to use this, if you want to get actual measurements from this image. So, I don't know if timestamps are also often wrong. I don't know if any of you have looked into this, but the measurement information we get from GPS and it's not always GPS, but localization and timestamps, it's hard to trust them. And I'd love to be able to, but it's just not the case right now. And many images don't have these, historical photos, paintings. We'd love to handle paintings too. We need to be able to do this from vision as well. So we want pixel accurate position and heading. We want to know, like I was just saying, for every pixel in the image, what object does it belong to? Okay? So we can use this sort of existing metadata like GPS as a rough guide, but we need to be able to do better. Okay? So I'm going to sort of sketch out a story of how we're starting to do this using large-scale computer vision. The sorts of things we did in Rome in a day that Mark was mentioning, but at an even larger scale. We want to build 3D models of the entire world that we can use for this task of localizing new photos. So I'll talk a bit about this, how we can build a global database of geometry for this task, how we can get people to intentionally contribute photos rather than just sort of sneakily downloading them from Flickr, how we can calibrate new images given this data, and starting to get into some applications using other georeferenced data sources like Google Earth 3D models or time-stamped weather data for this, for vision applications. Okay, so I'm going to start out by talking about the sort of core geometry, sort of scalable geometric reconstruction from internet photos. So when you want to recognize the location of an image, there's a couple ways you can do it. One is you can compare it to other images, sort of 2D images, and see which ones it matches. Google search by image does a sort of similar thing to that. What we're doing is slightly different. We're taking images and matching them to 3D models. And that's what's going to sort of form the core of this technique. So towards that end, one of the things we're doing is trying to take all the photos in the world and sort of fitting them together as 3D models. And it'll become sort of clear what that means as I go through the next few slides. We've developed, sorry, go ahead. Yeah, question. We want to derive, so the question is, am I talking about reconstructing 2D projections of 3D models?
You have to match the picture to 2D projection.
That's correct. Yeah, exactly. We want to find the viewpoint of the camera by finding how it should be situated in the world such that a projection of that 3D model agrees with the image. Yes, that's correct. And to start out, we're going to do the inverse of that, actually. We're going to take a collection of photos and then recover the 3D geometry of that scene from that photo collection. So here's an example with a set of photos of the Colosseum that I got from Flickr. We've developed algorithms that will take those photos, sort of turn the crank, and then output geometry. Okay? So that geometry tells you, for each of the photos in that input collection, photos of the Colosseum on Flickr in this case, where exactly was that photo taken? So that's what all these little wireframe pyramids are. Camera positions and orientations. And what's the rough geometry of the scene? That's this point cloud that sort of looks like the Colosseum, but a very pointillist version of the Colosseum. That's what we reconstruct. Okay? We can also densify this. This is sort of a dense model of the Colosseum produced from a set of internet photos. And again, you can see the reconstructed viewpoints down here. We're not using GPS or any other sort of sensor information, except for we do use the focal length if we have it. Sometimes that's in the EXIF tags. Yeah, very useful. How zoomed in is the image. But even though we don't have GPS, we can still produce this pretty nice reconstruction. It's not quite laser quality reconstruction, but it's getting there. It's getting closer. So this is produced completely automatically using these internet photos. Here's another example. I'll show a sparse reconstruction in just a moment. These are photos of Dubrovnik, a city in Croatia, sort of beautiful medieval city, old city of Dubrovnik. We run it through our software, and what the output is this. So this is animated. Again, those black wireframe points are reconstructed camera view points. So where was that person standing when they took their Flickr photo? And so here's sort of a fly-through of this 3D model where you can see this ghostly version of the city of Dubrovnik flying past as we move, as we just do a fly-through. So you can see all sorts of buildings. This is a church. We zoom out and see more of the city. You can see a bunch of photographs taken along city walls, sort of looking down on rooftops in the city. And here's a different view looking out across the city towards the mountains in the background. So this is the geometry we've reconstructed automatically from these camera viewpoints. Question, yeah.
This collection of photos by hand or by the noise GPS data? How did you choose that?
These photos were selected by searching for the tag Dubrovnik on Flickr, and then downloading whatever people had tagged Dubrovnik. Which often, the question was, how do we get these images? Often, things that are not actually Dubrovnik are tagged Dubrovnik, and vice versa. So as part of this process, we have to filter out a lot of noisy images. I think there's a question here first. Yeah. I'll talk about, so the question is, why is it a ghostly version of the city? If there's any aesthetics to this, it's accidental. But the part that's not accidental is that only parts of the city that were captured in photos are reconstructed. So if, yeah, partly. It's stuff that people have paid attention to that has gotten reconstructed here.
Therefore, things like the point line on a brick wall, the position is plus or minus a certain number. So that's what kills you. If that's what's going on, that will kill context.
So the question is,
precision here because the accuracy of reconstruction.
Good question. So the question is, why is it fuzzy? It's partly an artifact of how we're rendering it. It's just, the OpenGL calls we're making. And it's partly what you're saying, which is that a point is only reconstructed up to a certain accuracy. Right, depending on sort of the local appearance of that point in the images that see the point, okay? In a complicated way that's hard to sort of explain in the short time here. But the other thing is it's not completely dense because we only reconstruct points that are sort of salient in an image. If there was a completely white wall with no features on it, we would not reconstruct any point, or if anything, just a single point, big point at the center of that wall. But if something is very detailed, like intricate brickwork, we would reconstruct tons of points there. Question, yeah. In this image, well, so we input, I think, about 60,000 images, okay? All the images of Dubrovnik we could find. The output was, I think, about 6, 7, 8,000, somewhere around there. Because the others were things like, oh, it's somebody's shoe, or here's our plate of food, which didn't match any other image in the data set, okay? Yep. One more, yeah, I'll take one question now and then move on, yeah. So the question is this accessible, and is it something that will be updated every so often? There's two things. There's the software that created this, and there's the model itself. So the software is available for anyone to try. It's called Bundler. I've released that code. There's also, Microsoft has sort of their own version of this called Photosynth that you can use to create 3D models. And since this work, there's been a few other products. One's called Visual SFM, sort of free downloads that can create these models. We've released some of these models. I don't think we've released this particular one, but we share sort of static versions of these. We're currently not updating them, but my dream is to sort of have these models that are constantly being updated as new photos are added. That's sort of the eventual goal. Sort of have this computer listening to the world's photos and sort of figuring out how things are changing. Oh, this building is not there anymore, so our model should be updated. That sort of thing. Okay. Oh, we have one more question. Sure. It's a lot. So the question is how much computation time is needed. It's pretty intensive. We can process about 100,000 photos in a day on about 300 machines. So it's, that gives you sort of an idea of the scale. But we've been constantly trying to improve that. There's a bunch of ways we can make it better. Okay, so I'm going to talk a little bit about how we do this recovery of geometry from these unstructured photo collections. And the whole point of this is to get back a much more structured representation. So you put in a bunch of photos, and what you get back is something that has you can make actual measurements with. It's 3D information. But how do we get that 3D information? So there's a few important pieces of this puzzle. One is, so you have these images. How do you figure out the 3D geometry of the scene? The first thing you need to know is what points in the images are the same point in 3D. Okay, so this is correspondence problem. How do you figure out that certain points of these are 2D projections of the same 3D point? Okay, so you need to know some form of correspondence. In the old days, photogrammetrists would click on these points manually, but now we have sort of not completely foolproof, but somewhat automated techniques for this. And a very important development has been in computer vision, the advent of very powerful features that are very stably detected in images. What I mean by feature is a particular point in the image that looks salient and that you can reliably detect even in images that are transformed. The lighting's different or the camera position is different. So Sift is sort of the most famous of these, and it's the first that really worked incredibly well and well enough for these internet photo applications. So what you're seeing here is a set of Sift points. I put in an image this is part of the Trevi fountain, and it returns back thousands of little features, little patches in the image that look salient. Okay, things like corners or blobby things that not completely blank surfaces, but things that have structure to them. Okay, so you put in the image, and out come these Sift features. That's just a black box. You do this for all the images in your collection. Here's some images of the Trevi fountain. We've detected Sift features in them. Then you compare all pairs of images and look for matching Sift features. Okay, so that sort of builds a graph on top of the images. These images match. They have features that look similar. These images don't match because that's a plate of pasta and this is the actual fountain. And it's smart enough to tell that those things don't match each other. Those features in those images don't match. Okay, so you get back this graph. Okay. Here's an example of sort of matching Sift features between two images. It's incredibly, if you ever need to detect features, you should try Sift and match features between two images. So these little squares are features, and the colors mean they're the same feature between the two images. So you can see that they're pretty well found matching features, despite the fact that these images are very different in lighting. That image has a bunch of pixels that are not the fountain because they're heads. And so it did an amazing job, and most of these are correct. There's one on the shirt that can't possibly match any feature in this image, but that's okay. We can tolerate some amount of noise in this feature matching process. Okay, so that gives you an idea of what these matches look like. Okay, so we're finding the same 3D point in several images. So here's a larger version of an image graph. Okay, this is a graph where each image is a node, and images are connected by an edge if they have visual overlap, if there are matching Sift features, okay? So this happens to be a graph of images of Rome. So there's the sort of Colosseum part of the graph. This part of the graph is mostly images of the Colosseum. And then over here, this is part of the Forum, or possibly the arch near the Colosseum. Down here is this ugly building, I think they call it a typewriter, in Rome. And then the Pantheon's over here in sort of its own cluster, because there's no path of photos that takes you visually from the Colosseum to the Pantheon. It's just, they're too far apart. People don't walk between them and take photos every meter, which is what we'd need to sort of connect them in this graph. So this sort of gives you an idea that we're finding this sort of topological structure in the image set. It's not geometry, but it's a step towards it. This just tells how the photos are connected to each other in a visual way. Okay? So then the second key ingredient, once you have this correspondence, is this big optimization problem. The optimization that takes the correspondences and actually tells you the geometry of the scene. Okay, so we want to take that image graph, that messy thing that connects images, and get actual geometry. So here's a 3D version of the Trevi fountain. And that's a problem a very old problem in computer vision, actually, called structure from motion. Getting the structure of the scene from these cameras from different viewpoints. And it's sort of a chicken and egg problem because, the Greeks knew how to do triangulation. If you have cameras and you know exactly where in the world these cameras are, and you have 2 points that match, well, then you can just triangulate them and find the 3D point that they correspond to. You can also do the reverse. If you have points in 3D that you know they're 3D coordinates, and you have an image of them, you can figure out the pose of the image. But here we don't know either. We don't know where the cameras are, and we don't know where the points are. We have to sort of figure out both at the same time. It seems like a difficult problem, but it's actually doable. There's enough constraints that these correspondences give you that you can derive the 3D structure. It's not an easy problem, though. So this sort of gives you a picture of what, at a very high level, is going on. So we have these images with corresponding points in this toy example. And we don't know where the images were taken, and we don't know where in 3D these points are. But we know that whatever the answer is, it should meet certain constraints. So what we want to do is solve for a set of 3D points, here labeled P, and a set of camera parameters. So every camera has both a rotation, so what direction it's facing, and a position, where in 3D it is. We want to solve for all of these parameters such that if you project a point into an image, it projects where you expected it to. So that's the key constraint here. You know that whatever the configuration of all these cameras and points are, a point should project close to where it appeared in an image. That's sort of the law of perspective projection. Okay? So this turns into an optimization where you want to minimize the disagreement between where you saw the points and where they get reprojected to. It's not that important to understand the details, but what is important is that this is a huge optimization that's very nonlinear. It has tons of local minima, and it's just messy and gnarly to solve. Right here, it sort of looks small here because we only have 3 cameras and 7 points, I guess. 1, 2, 3, 4, 5, 6, 7. Yeah. In reality, we'll have many, many thousands of cameras and possibly tens of millions of points. So it's a huge search space to try and search for all possible configurations of points and cameras. That's why this is a hard problem. So the way that sort of up till now we've solved this problem is to do it a little bit at a time. So we take all these thousands of cameras, find a few of them, reconstruct a little mini scene, and then sort of add stuff to that scene greedily and build up this bigger and bigger version of the reconstructed scene. So here's a picture of that for this Dubrovnik model I showed earlier. So what's happening here is you're seeing sort of a time lapse, not a real-time time lapse. This really took many hours, but what you're seeing is sort of the city taking shape. It's sort of appearing out of the ether as this reconstruction, this incremental reconstruction process is happening. Okay, so let me show that one more time, maybe a couple more times. So parts of the city, cameras are appearing, points are appearing. That's the flavor of this reconstruction process we're doing. So things sort of shift around as more cameras are added because you have more information to work with. And at the end, the entire city is sort of, or whatever you can reconstruct from this set of images has appeared. Okay, and sometimes little details get filled in, and sometimes the entire city changes, just depending on sort of the order in which cameras are added to this optimization. So this is what I'll call incremental structure motion. This is sort of a very standard technique. It works very well. It's something I've used a lot, but it has a lot of problems. The primary problem is that it's very slow. You do this every time you grow the, oops, I should get myself one out. Every time you grow the reconstruction, you have to do this optimization, which takes a long time, okay? So, and if you have all the photos of Rome on Flickr, for instance, all 3.6 million of them, then you don't want something that scales very poorly, or you're going to wait, 100 years for your algorithm to finish. So, just for fun, here's what 1 million images of Rome looks like if you made every image a pixel in size and tiled them into one ginormous mosaic. So somewhere in there is, the Trevi Fountain and the Pope, whatnot. All sort of interesting things in Rome are represented here, and many uninteresting things as well, I might add. There's runs of photos, I think, taken by the same user that sort of have the same color. Maybe they were testing their camera, I don't know. So here's sort of, we've recently moved to a different view of this problem, which is a more global view. So this incremental structure motion, it sort of builds things a little bit at a time. But we've recently switched to something that tries to solve the entire problem at once, using very sophisticated modern optimization tools. I'm not going to really talk in detail about those tools, but I'll give you sort of a flavor of what this problem looks like, okay? So we have our image graph, images connected by edges. And we're going to treat this as sort of a physical system, right? So the images are going to be nodes which are connected to each other by certain constraints. And you have to sort of solve for the assembly of all those images that sort of satisfies those constraints. So you can imagine this is a set of Tinker Toys, as I'll talk about in a second. And so we have this graph with these certain constraints between cameras, and maybe we have some geotags that we don't quite trust, but we want to use them where they're helpful. Okay, so I'm going to call those unary constraints. They're things we know about an image without having to look at any other image. And so we're going to label each camera with a pose, a 3D position and orientation, such that all of these constraints are satisfied as well as possible. So, so imagine I just dumped a bunch of Tinker Toys in front of you, okay? And each of them has a label 1, 2, 3, 4, 5, 6, 7, 8 to maybe 10,000. And then I give you a bunch of instructions that say Tinker Toy 13 and Tinker Toy 17 need to be in this relative position with respect to each other, okay? At this angle and at this distance, and pointing in this relative direction, okay? So, and then for some blocks I tell you, this block should be at coordinate, 100, 200, 300 in 3D space, okay? So I give you a bunch of these instructions, and then I tell you, well, try and put the Tinker Toys together in such a way that these instructions are satisfied as well as possible. And by the way, some of the instructions are lying to you. I may have given you a geotag that was 10 kilometers away from the true location of that image, okay? So you have to deal with instructions that are trying to deceive you. That's the sort of flavor of this problem, the noise and the geotags that we deal with in real life, okay? And also, we have thousands of blocks, and we have millions of these edges that you need to add, okay? That's what we're dealing with. But at a very high level, you can imagine as this sort of simple Tinker Toy assembly problem. Just follow the instructions, and you'll be a winner. So, where do these sort of pairwise constraints come from? How did I tell you that camera 13 and camera 100 have this relative configuration? Well, they come from looking at two images and automatically determining sort of the relationship, the spatial relationship of these two images. So if I showed you these two images, you could probably guess at if this is where the first image was taken, where the second image had to have been taken. You could probably say, okay, well, the camera was probably turned this way a little bit, and maybe it was taken a little bit to the left and forward. Given enough time, you could probably do that reasoning just by looking at the two images. So it turns out computer vision can do that too. If you can if you know matches between the images, say Sift correspondences, then you can figure out the relative pose of these two cameras, okay? So you can tell that, if camera 1 was taken here and looking in this direction, then camera 2 must have been taken here and looking in this direction. But you don't know necessarily the heading of any of the images. You don't know it was looking north. You just know that relative to the first image, this image was taken looking this direction, okay? So it's all relative. These things could move as a whole in any which way, as long as they have this relative configuration. Yes?
Relevant that might have to other.
So the question is, has anyone studied what features are most photographed and how that can contribute to other fields? That's sort of what that work I talked about at the very beginning in clustering these geotagged photos is doing. One thing I didn't mention is that they looked at the visual connectivity and tried to figure out, well, what photo is the most representative of this collection? What photo appears the most times? What? Well, so that little image I showed you, the little thumbnail that was in each of those little boxes, that was the most sort of popular photo, as judged by it's the photo such that the most other photos are similar to that photo, if that makes sense. Well, first of all, you probably wouldn't. What it would probably find is near duplicates, because that's where you probably have. That's probably the only place you have a lot of overlap is between. It's potentially useful in showing fraud, like if photos doctored. So I think there's a whole area in sort of meta-analysis of how people take photos that I'm not really qualified to work on, but I would be very excited to work with somebody on. So that's what I'd say about that. Yeah. So we have these constraints built up, and that sort of builds this graph of these Tinkertoy blocks where we have connections between images. We have these pairwise camera transformations on edges, and then we have any kind of sensor information like GPS or heading information labeling each node. These are the instructions that I talked about. 3D points fold in there somehow. I won't talk about that. But here's another way of visualizing the graph. Picture is connected by edges, and some of the edges have GPS tags. Okay? And then from that, again, we turn the crank, and we get out geometry. By the way, there's other ways you can sort of try and get information about the camera parameters. So if you can detect a vertical vanishing point in an image, that tells you how tilted the camera was and how twisted it was. So twist meaning, was the camera straight, as most people take it, or was it taken at a weird angle, like 45 degrees? So you can figure out just by looking at an image sort of certain facts about the orientation. Question? So the question is, how important is it that it's an image of an architectural scene where you find things like lines, or standard architectural scene? You won't be able to detect a vanishing point reliably if there's not straight lines in the image. That's we're sort of, the way this works is detect edges in the image, connect them into lines, find strong lines, see if a lot of them intersect at the same place, and call that a vanishing point. If the building does not have that property, well, I guess what I'd say is our algorithms are robust enough not to get fooled into thinking there's a vanishing point that isn't there. It would just say, I have no idea where the vanishing point is, I give up. Okay? You're free to do what you want with this image, but I'm not going to help you. So we're pretty robust in that sense. Yeah, question? We don't, so the question is, do we use color information? And the answer is no, we don't use color information. That Sift algorithm I talked about, that works on this grayscale image. So you think color would be amazingly helpful, but really almost all the information is in the grayscale pixel, or sufficient information is in the grayscale image. Yeah. Yeah. Color is a very subtle and crazy thing that is affected by white balance, illumination. This, same viewpoint might have very different color histograms. Question? We use all the Sift features. The question is, do we use all the Sift features? Yes, but some of them naturally fall away because they don't match anything else. So a lot of Sift features are just, oh, it's this person's eye, which never appeared anywhere else in the data set, so it just sort of gets lost during the matching process. Yep, it's automatically able to find the ones that are good and the ones that are not are sort of meaningless for this task. Good question. The question is, what about shadows? Shadows don't matter all that much. Sift is pretty robust to illumination changes. So we're not fooled by shadows. Okay, so here's sort of a toy version of the graph. Here's a slightly bigger graph that's from the Acropolis, and it shows you sort of the structure of some of these image sets. So what often happens is you have a very tightly connected part of the graph because everyone takes the same photo. And then you have a part of the graph that's very weakly connected because only a few people bothered to take a shot that saw the inside and the outside of the Acropolis in the same image. So it's very common to see these very non-uniform graphs where you have lots of clumps connected by sort of sparse connections. Okay, so we have all these. So we have this nifty optimization technique that uses these sort of newfangled discrete optimization techniques to to very quickly search the search space of possible configurations of cameras and points. So that's sort of the key here. We can use very powerful discrete optimization techniques for this problem. I'm not going to go into it, just to sort of emphasize again the scale of the problem we're solving. We could have millions of nodes in our graph, both cameras and point nodes, and and several million edges. So this is a very big optimization. It's faster than the old incremental approach. We can solve this globally using a single optimization technique, but it's still quite a big problem to solve. So you have this big Hadoop implementation. It's very fancy. So I'll just show you a few results of this technique. I showed you the Dubrovnik one already. Here's a few others. This is a little closer to home. This is the Cornell Arts Quad reconstructed from thousands of photos. So sort of a beautiful campus quad fly through of the reconstruction. Here's a larger reconstruction of various parts of central Rome. So we're going to start by flying over the Colosseum, then through the Forum, which has all these cool Roman ruins, over to this viewpoint looking back across the Forum back to the Colosseum. You can see a bunch of other buildings sort of off to the side. So these are all images that were visually connected in one way or another. These are Flickr images, visually connected and reconstructed using these structural motion algorithms. Okay. As a byproduct, since we are using geotags, even though many of them are noisy, we're robust to that. So the output reconstruction is automatically geo-registered with the world. So that's very important because that means that any image we can add to this is also geo-registered with the world. And so we can figure out the exact camera parameters of that image as well. Here's another example. These are images where, in this case, the points reconstructed are red. The cameras are green, so you can see that the points line up with buildings, and the green points sort of line up with paths, except where people took shortcuts across the grass. Here's another reconstruction plotted on a map, the Rome one, and you can see that the Colosseum is where it should be, and various buildings line up with the map pretty well. So this reconstruction, I haven't talked about accuracy at all, but at least it's accurate enough to line up pretty well with the map. And so we're applying this sort of at scale to all of the landmarks we can get our hands on. So we've downloaded, at this point, millions of images from Flickr all across the world. And we're building as much geometry as we can from these images. So for all parts of the world, we're running this algorithm, and getting back 3D models. So there's Chicago, here's Grand Central Station. There's photos taken indoors as well. Here's the Tower of London. These are 3 of many thousands of 3D models that we've built so far. And again, these are not computer graphics 3D models. These are more like, computer vision 3D models, but they're useful for the task that I'm going to describe, which is localization of images. It doesn't always work. You can imagine computer vision is better than it was 10 years ago, but it still fails in interesting ways. This is a reconstruction of the Tower Bridge in London. Can anyone spot the problem?
Background, it locks onto the background, in the background, and flip it doesn't know which tower.
Yeah, I mean, the most obvious thing is this. Yeah, this is flipped. So I think it must have confused the left and right towers because they look the same. And it duplicated this guy over here. Well, sort of hard to tell from a close-up which tower you're looking at, so vision got confused as well. They're very white. The left-hand side.
Left-hand tower, the diagonal element.
This one.
Yeah, the left-hand, that one, yes.
This one.
That's not part of the tower, if I'm reading the picture correctly.
Well, I think the problem is that it's 2 of them, when it should only have 1.
No. There's something in the actual image. There is one.
Oh, you're talking about the...
Yes, but it's showing it as part of the tower.
You mean something back here?
That. You wanted to step there, that.
I see. There are things, yeah. I agree. There's probably multiple things wrong with this image.
It doesn't pick up the stereo effect. That would show that the other item is in the background, not part of the tower.
Yeah, I should do a fly-through so you can see more clearly what's what. Here's another example, which is not obviously wrong, except when you look at it from the top. This is the Notre Dame Cathedral. What happened here is that, well, if you've been to Paris, this should be the River Seine, and there aren't buildings in the middle of the River Seine. What happened is that there's a steeple which has an 8-fold symmetry, and so there's a 45-degree copy of part of the Notre Dame Cathedral that got slapped onto the real one, and the whole city of Paris is rotated 45 degrees and put down around it. So anytime there's something that's ambiguous as to which direction you're looking at it from can cause problems. Here's sort of the worst example I've seen. This is St. Paul's Cathedral, where there's both a dome-shaped point. There's a dome-shaped set of points, and there's a dome-shaped set of cameras. But these dome-shaped things should be on top of each other because you take photos from the dome. But they're not because, well, actually there's many, many things wrong with this. One thing that goes wrong is there's a tower with a clock with 3 sides showing a very similar clock. And so all 3 of those copies of St. Paul's get folded up together. And so it's like a weird Mobius version of the universe. So the question is, why don't we throw data away if we know that it's wrong? What the problem here is that the Sift features that we're matching, the towers are so similar that it matches Sift features between faces of the tower. When those points really aren't the same 3D point, they're just 3D points that have to look very similar to each other. So there's no way that it knows that whether it's seeing something that looks like the same 3D point, or whether it's seeing 2 or 3 or 4 or 5 copies of something that looks very similar. So the question is could we use, from unique features, could we disambiguate similar features? I think so, and that's something we're working on. I think that your intuition is exactly right. You should be able to tell that this is not the same thing because you see something you shouldn't be able to see from different viewpoints. Yeah, so this is a little bit higher level reasoning than we currently do, but I think that's probably what we need. Question? Were these? It's not adding images. So the question is, would adding more images help? I think, and I don't think it would. It's really that it can't tell the difference between. What's really happening is that it needs to be able to distinguish between very similar objects, and it can't do that. And that's regardless of the number of photos. Or you could come up with more unique Sift features that, if the pattern of dirt on one thing is slightly different, it would pick that up. GPS tags should help, but they're not. So we don't trust GPS tags very much. So it's this weird interplay where we have to trust the vision data to some extent and trust the GPS tags to some extent, and they're lying to each other, and it's hard to figure out which one is telling the truth, and it ends up with the wrong answer. So it's difficult to know who to trust in all cases. Yeah. Yep, so the comment is that could knowledge of symmetry help this? I think definitely. It's not clear how to encode that knowledge into the system, but if there is a way, I think it would help it a lot. Yeah. Yeah. Symmetry groups, we sort of have to know about that, yeah. Yeah, question. So why is GPS data noisy or poor? There's a bunch of reasons. Frankly, not all of this is GPS data. Some of it is manually entered by Flickr users. And it's not always clear what is manually tagged and what's machine tagged. GPS is also, for whatever reason, either you're in an urban canyon or you just turned on your camera and it hasn't quite established a lock, so maybe it tagged it with the last place you were. There's a number of ways that can screw up. And so it's not quite good enough that you can trust it for a variety of reasons.
For example, in Manhattan, they have to give up GPS on buses.
Oh, because of the tall buildings. Yeah.
So bad that they have to use edge recognition.
Yep. So that's, in cities, indoors is also a problem. Question. Yeah. Yeah. So the question is, why not use street view or aerial views to help here? And the answer, we would love to. Yeah. We just haven't. It's a question of sort of both data access and we're lazy, I guess. Yeah. Yeah, I'll get to that in a minute. Yep. Okay, let's see. I know you had your hand up for a while. I'll take one more question and then continue for a few minutes and then, yeah. Yeah, it's sort of time intensive because video, 30 frames per second. There's probably smarter ways to handle it. But yes, video is very interesting too. And I think video, I can't quite tell whether video is going to take over pictures. It seems like it's not going to happen. There's something special about pictures that people like. So we've been satisfied enough with pictures. There seem to be enough of them that we haven't started using video. Okay, I just want to show a demo of sort of other things you can do with this. So this is something I did a few years ago now, where I want to create sort of a visualization of these data sets. So what you're looking at here is an overhead view of the Statue of Liberty, a reconstruction of the Statue of Liberty from Flickr images, a few hundred in this case. And so we can sort of fly around the scene. You can see photos taken. These are photos that people took on the boat ride, ferry ride. These are photos taken on the actual island itself. I think I saw the statue out there, maybe on a higher floor. But it's cool. It's visible from this building. But not only that, you can actually fly through the scene and sort of use other photographs as your virtual camera. Okay, so as I fly around, images will show as soon as I get close to the set of Flickr images, and they're sort of renderings. I'm stealing them to render my virtual view. So here I'll click on a photo, we'll fly down into the image set, and you'll see that now it's showing me images that are close to my virtual viewpoint. And the reason we know they're close is because we've reconstructed the geometry. All these images are in the same coordinate system. So I can just treat this like my virtual camera. I can zoom in, and as I zoom into the statue, it will load a higher resolution view so I can see the image of the right resolution. I'll zoom back out. I can also rotate around the object, and it will show images from the right viewpoint because it knows where those images were taken, and it knows enough about the geometry so that it can align them up as I fly around. And there aren't a whole lot of images of the back of the statue, so I sort of get empty view there. But this sort of shows you sort of the power of combining all of these images together, in this case for visualization, and showing what a place is like. And these images are very, very different weather and lighting, but they all fit together through Sift matching, and you sort of get the range of all experiences of the statue. Okay, so that's sort of the first part, and the other parts I'm going to go through very quickly because so necessarily, but there's fewer slides there, which is fortunate. So just a couple of different projects that sort of fill in, well, some of the gaps in this process we're doing, quite literally. So if you look at photos of the Colosseum that are on Flickr, there's very few that are not looking at the Colosseum and are in a rarer view. So I'd sort of like to be able to build a model of everything, including this restaurant or whatever that no one takes a picture of. So I'd like to be able to fill in gaps in these reconstructions. The backside of the statue, well, a photo exists of that, but not many of them, and not enough to connect it up to the front of the statue. Uninteresting places. Maybe this is the only photograph on Flickr of this alley in Rome. And also building interiors. Places where photos tend to be rarer. So you can do some things to fill in the gaps. You can use aerial images, as was suggested, or street view images. Here's a street view image, which has pretty good coverage of Rome. But you'd like to be able to do this sort of at scale, very efficiently and very quickly. Whenever something changes, you would like to be able to get a new photo of that so you can update your model. Okay? So the idea is, why not use people who are already walking around with cameras to do this sort of task for you, so you don't have to drive there yourself. Plus, you might not know it changed, so you sort of want photos all the time from everywhere. So we built a game called Photocity. This was with collaborators at University of Washington, where we sort of made this photo capturing process into a game, where if you take a photo of something new, then you get points for that. And literally, 3D points that you create, new 3D points in our model, become virtual points. They're not worth anything except karma or kudos. But it's worth it to play the game if you're a certain kind of person. And we did get there. I'll talk about some of the ways we incentivize people to play. Part of it was just they're interested in the game and they're interested in seeing these models grow. But there's other incentives as well. So the idea is we start with some models that we created ourselves just from a few photographs, and then at the borders of those models, white flags appear, and those are flags you need to capture. If you capture a flag, you get some points. And if you capture enough flags around a model, you capture that model and you become the landlord of it. Okay? So there's both models and flags, and these are things that you can capture in the game. Okay? So the idea is, over time, more images would be added, people would play, more complete models would be created, and eventually this would cover, in this test case, the entire Cornell campus. So we did this as a competition. There's another incentive. You were competing against another school, University of Washington versus Cornell. Seeded a few models. They're not traditional enemies, I know. But anyway, we created a company. They're about the same size, which is good in terms of number of buildings. So we wanted to see, in 3 weeks of gameplay, how much of the campus could be reconstructed using photos contributed by players, who are mostly students in this case. So here's the students could also seed new models, like take pictures of a new building and add that to the game. So here's the state of play at University of Washington after a few days. At the end of 3 weeks, we had, I think, nearly 100 buildings covered, most of the buildings on campus and a few that were not on campus. Similarly with Cornell, most of the buildings were captured. At least partial models existed after the 3 weeks. And so, so Cornell actually won, let's see, by virtue of many more points created, 3D points in the world, even though they took fewer photos and had fewer models reconstructed. So it turns out Cornell students were better at exploiting features in the game where if you take close-ups of very detailed texture, then you're going to create a lot of 3D points because they figured it out. They figured it out. So they were more efficient in photos per point, and by that metric, they were deemed winners. But in any case, we got a lot of models out of this. You know, many more photos than were available when we started. If you look at photos on Flickr, so if you look at the actual gameplay, this is sort of number of points over time. Blue, purple is UW, red is Cornell. Sort of seesawed for a while. There's some, you know, as one took over, the other one took more photos and so on. And eventually Cornell won because they found later on how to exploit the game. But okay, so anyhow, here's a reconstruction of one of the buildings at Cornell that resulted from this process. A fairly complete reconstruction. Again, much more complete than we could have reconstructed from Flickr photos alone. So here's sort of a fly around of this entire building. It's like sort of an iconic building at Cornell with a clock tower. Here's the winner of the game with this prize we created. A winner, he contributed the most number of photos out of any player. I think over 10,000. And we gave him a laser-etched cube with the model that I just showed you engraved inside of the cube. Yeah. So here's a few other models of nice-looking buildings at Cornell. You know, some people got into it. Many players gave up after contributing a few photos because it's actually hard to. It's not the most obvious game to play. You have to sort of try it a few times to see what happens. If you take a photo that doesn't match anything, we don't know where it goes in the model, so we don't know how many points to give you. So it takes some time to sort of get into it. But people who stuck with it tended to get addictive. And one of the addictive things was seeing the models grow over time. So people would upload 1,000 photos at night, and in the morning they'd be very excited to see all the different things that they had done with those photos. We didn't reprocess orphan photos, so they never got any points unless they uploaded it again later. Yeah. That would have been a coup if they had, if they had. That would have been great, I agree, or a blimp of some kind. Yep, maybe in version 2. Question? Yeah. Originally, we wanted to encourage cell phone use because the idea was you could play the game as you're walking around, but people didn't do that, or most people didn't do that. Most people did go the digital SLR route because they discovered that the better the camera was, the more likely they would get more points. So what they ended up doing was they would go out and take 1,000 photos and then upload them in batch. Yep. The CRO. Oh, that's very, yeah. We didn't really, there are a few times when the police got suspicious. Okay, question over here, yeah.
Are you taking ways of mapping data or figuring out, like you said, location? How are you doing?
Yeah, so if we have no metadata, we can figure it out. So that's part of the geometry. Even the focal length we figure out. Even radial distortion parameters we figure out. Yep, all that's automatic. Yep. That's the beauty of computer vision. It's not secret, but it's not.
For example, you alluded earlier to this idea of time over space, photos over time, glacial melting, and building moving, and that kind of stuff. had images that came from an analog camera that were filmed and that kind of stuff, how would you pair those up? You would obviously know the location, but
as long as
what if you had the entire history of photography of New York City from film?
yeah.
And had to map it to the current time.
So I should make one distinction here, which is that we can compute, if we don't have any, let's say you gave me a photo collection without any geotags at all. I'd be able to still give you geometry, but I couldn't tell you where in the world that model lives, okay? It could be in Alaska or New York City or Mexico. I have no idea. It's just, relatively speaking, I know where the cameras are, but I don't know where it fits in the world. So I do need some geotags to tell me where it fits in the world. Oh, well, you need one to know, you need one reliable one to tell, you need, ideally you'd have 3 reliable ones, because there's also orientation and other things, yeah. Okay, question. And we have to wrap up fairly soon. 10 minutes, yeah. Correct. Nope. I would love to incorporate those. Yeah. It seems like there's no place I can go on the internet and download all of them in the world. But yeah, like building footprints I've seen for New York City. If people have ideas, if people can point me to the right resources, I'd love any GIS type data. I'd love to get my hands on. Yep. So let me just get through the rest of this talk, and then there may be time for a few more questions afterwards. So I'll ask one question. Where was this photo taken? Yep, it was in Havana. I heard that. I'm not going to ask you the other ones because we're running out of time. You'll have to think about that later, although I already showed you the answer. So what we're able to do now is by matching to these models, matching new photographs to the models, we can tell exact camera parameters of new images. So here's an example of an image we matched to our row model, and it thought about it, gave back a position and orientation, and said this image was taken here, looking in this exact direction. So we're getting very accurate pose estimates by doing this matching to 3D model process. We also get the horizon line, just from knowing the geometry of the image where it was taken in the world. And this, I think, is very useful for being able to relate this image to GIS data. Like if you had a map of road beds in Rome, you could just project it into this image, and you know which pixels in this image are roads. And then for image understanding tasks, that would seemingly be very useful. It solves a number of problems. Here's another image. Here's its field of view. If you knew, for instance, what the bus schedule of buses in Rome are, you could maybe tell approximately what time this photo was taken. So there's a number of interesting things I think you can do once you have once you can recover exact pose of an image, and sort of relating it to all the stuff that's in Google Earth and all the stuff that's in New York City's GIS database would be very interesting. Here's just a few other examples. This sort of shows you the accuracy with which we can localize images. So this image is by the way, we didn't know any GPS for this image. It just sort of figures it out by matching to these models. It knows that it was taken here, and you can see that it's looking through this fountain, and indeed the image is looking through that fountain. So that's sort of the level of precision with which we're localizing the imagery. Here's a few other examples. It works indoors as well, since it's just based on computer vision. As long as the models are registered correctly with the world, this works. Okay, so that's sort of, now that's the system we're building for starting to calibrate these new images. I just wanted to mention one other thing. Why would you want to do this? Here's an example of a geo-registered data source that we're leveraging here. So I love this. This is really cool. I'm glad someone did this. But you may have been to the monument in London. This is the monument to the Great Fire of, what was it, 1666, when a lot of London burned down. Christopher Wren designed this monument, built it. It's pretty cool. I think it was originally designed to be a telescope, but it never worked. It was a telescope that's always pointed at the same place, but turns out there was too much traffic around, like, I guess, horses and so on, that it was too shaky to work as a telescope. The spiral staircase, you would see how it could be used as a telescope. There's an artist called Chris Mies Andrews who put a panoramic webcam at the top of this thing and filmed every 30 seconds, took an image every 30 seconds for several years, a high resolution image. Here's what 1 day's worth of that imagery looks like. From midnight to midnight, you can see weather. You can see the shadow eventually of the tower of the monument going across the city. It's very beautiful. I'm really glad this data exists. But we're just thinking of sort of crazy things you could do with this. And what we came up with is sort of the world's most convoluted way of telling time, which is to take a photograph from about the same location and to correlate it. Once we know the position and orientation, actually the orientation is more important, to correlate it with the clouds visible in that time-lapse video. So we know enough about this image to segment out the sky pixels. So here's the sky pixels. And then you correlate it with, we happen to know the day this photo was taken. You correlate it with the sky in this image. In both cases, north is north, up is north. And there's a clear peak, and so you know that this photo was taken at that time because the clouds match. So it's a cloud matcher for knowing time. And so if you match the photos, you can see that they don't align exactly because, well, first of all, the photos aren't exactly in the same place, and also clouds can move a lot in 30 seconds depending on how fast they're going. But it's a believable match, and it's clear enough that you can see that they're indeed the same cloud. So, there's, just to wrap up, there's a lot of interesting challenges here. This is sort of just the first steps in leveraging this internet data for useful measurements. Okay, we've done sort of the first thing, which is figure out location. We're starting to do time as well, but it's an ongoing challenge. So scalability is still a big challenge, doing this for really the entire world and not just small percentages of it. Dynamic scenes, how do we model things that are changing? Can we get people to help with things besides just taking pictures? Can people help annotate and sort of understand this image data, sort of like the Galaxy Zoo example? Changes that occur in the actual structure of the world, can we model those? Like, in China, before the Olympics, lots of things got built, so it'd be interesting to try and understand that progression from photos. Interiors are an interesting challenge too. They tend to look very different from exteriors, and so there's different vision challenges associated with them. We started to do try and match images over time. There's all these beautiful paintings and etchings from all the way back, at least to the, I guess, 15th century, were done perspectively correct, at least by some people. So here's some examples of old etchings and photographs. Photographs of different times. These are things that are very challenging for our method right now because the features look very different. So we're starting to work on using symmetry as a feature for telling that two things are the same. I'd like to thank all the students who I have the pleasure to work with and collaborators. And with that, thank you very much. And if there's more time for questions, I'd be happy to take them. And more information can be found there. It looks like it's 7:56. I know we have to be out of here by 8, so maybe I'll take questions offline. One question. I think you had your hand up first.
But what about for your rotational system? Like, you know that second frame video kind of has a full on that helps.
So what you'd have to know is that so the question is, can we use video to help disambiguate rotational symmetry? I think so, yeah. I mean, you'd have to know that when you move to something that looks similar to something you saw before, that you hadn't done a full 360, but had moved not quite, you know.
Right. Video is 30 frames a second. You work out what magnification, excuse me, speak louder. You can work out since you've worked out the range from the magnification and other pieces of data, you can work out a reasonable velocity approximation of how far the camera will move frame to frame.
Yeah, I agree with that. You can work it out. I think the bigger question is, I have no idea how people take video. Like, what are these 72 hours worth of video on YouTube? First of all, can I find I'd like to not do it myself. I'd like to be able to find videos that already exist. How do I find the video? And do people actually take video walking around an object? Or if I'm at the Pantheon, how do I take a video? Maybe that's an interesting question in itself. How do people tend to take video differently than they take photographs? So I'm not convinced that the video data exists that will help with this, but it's sort of video is a very interesting space. Okay, thank you. Yep. Good. Bye.
Thank you all for coming.